Are you a student, hobbyist, or engineer trying to figure out oscilloscope bandwidth? Have you ever worried about choosing the wrong one? Too low, your square waves turn to mush. And too high, you're wasting money and adding noise. Now, let's settle this in 3 simple steps. Know your signal, set a target, and add headroom. Oscilloscope bandwidth is simply how fast the scope can follow a signal. The higher it is, the more detail you capture. With low bandwidth, the scope can't keep up. Fast changes blur together, and you lose sharp edges that matter. So how do we get this right? Step 1 is simple. Know your signal. Bandwidth is about how quickly a signal changes. To choose the right scope, focus on the fastest part of your signal, the highest frequency components. That might be a repeating tone, or it might be a very sharp edge. Once you identify the fastest part of the signal, that number becomes the baseline for setting your bandwidth target. Step 2, let's set a bandwidth target. Here's the rule of thumb. Choose a scope with at least 5 times the highest frequency you care about. Because signals are not just their fundamental frequency. They're built from harmonics, and without those, your waveform loses shape. So 5 times makes sure the scope catches enough detail for accurate measurements. Now, here's another useful check. Bandwidth and rise time are linked. A scope with bandwidth below 1 GHz has its own rise time of about 0.35 seconds divided by bandwidth. To measure a signal edge accurately, the scope's rise time should be at least 5 times faster than the signal's rise time. A shortcut is, pick a bandwidth comfortably ahead of your signal's fastest edge, so your scope shows what's really happening. Step 3 is also simple. Add headroom. Bandwidth math gives you a starting point, but signals are not always predictable. If your calculation is close to a scope's limit, go 1 step higher. That extra margin keeps you safe with fast edges and makes your scope useful longer. For example, if you calculate 50 MHz, don't just stop there. Jump to 100 MHz. Actually, many engineers aim for about 10 times the highest frequency to stay safe and future-proof. Now, what happens if you don't have enough bandwidth? Let's look at 3 common problems. First, you lose high-frequency details. Harmonics, spikes, and ringing get filtered out. A square wave that should look crispy now looks rounded, just like this one. Both screens are showing the same 10 MHz square wave. On the left, with 1 GHz bandwidth, the edges are crispy and the shape looks true. On the right, limited to 20 MHz, the harmonics are gone and the wave looks rounded and distorted. Second, amplitudes read low. By definition, at the bandwidth limit, a sine wave measures about 30% smaller. So if you put a 100 MHz sine into a 100 MHz scope, the display won't match reality. Here's a comparison. The blue sine is the true 100 MHz signal, while the red curve shows what a 100 MHz scope would display, about 30% smaller. And third, edges slow down. Every scope has its own rise time, and for a 100 MHz scope, that's about 3.5 nanoseconds. If you feed it a 1 nanosecond edge, the scope just can't keep up, and the signal looks slower than it really is. This illustration shows how edges slow down. The blue line is a true 1 nanosecond edge, and the red line is what a 100 MHz scope would show, stretched out to around 3.5 nanoseconds. But here's the flip side. More bandwidth isn't always better. A higher bandwidth scope shows more detail, but it also brings more noise you might not care about. For small signal tests, you can capture the signal first, then use a 20 MHz bandwidth limit to clean it up. Quick recap. Step 1. Know your signal. Step 2. Set a target, at least 5 times the highest frequency, or use rise time rule. Step 3. Add headroom. Too little bandwidth hides detail, and too much adds noise. If you found this helpful, please subscribe to our channel for next How to Scope. We will also be sharing product demos, unboxings, and more ways to get the most out of your RIGOL gears.